Dearest Dorsey. I am a junior biology major at Prairie View A&M University, and I'm currently enrolled in Professor Kevin Store's University Physics 1 course. And for my project, I will be going over the kinematic equations. I have a few questions set up here just so that I can assist with how to identify which equation to use. So before I get started, I would like to define a kinematic equation. A kinematic equation, or kinematic equations, there are a set of 4 different equations, which I have 1, 2, 3, 4 right here. There are a set of 4 different equations used in physics that assist with predicting unknown information about an object's motion. And with that being said, before I give you the equations, I would like to just note what some of the variables may mean. So right here you see V naught. V naught also mean V initial. You may also sometimes see V initial, or VI, V sub I, which means V initial. So that means initial velocity. V alone just means final velocity. Sorry. I'll put final velocity. You see X naught right here, or sometimes you may see X sub I, which is X initial. So initial position, I'll put initial P. X alone means final position, final P. T, of course, is looking for time, or means time. And then A means acceleration. So keep in mind, this is what the variables will mean once we see what the kinematic equations are. So the first kinematic equation that I will write is V equals V naught plus A times time. The second kinematic equation is X equals X naught plus V naught times time plus 1/2 AT squared. The third kinematic equation will be X equals, that equal sign look a little weird. X equals X naught plus V times time minus 1/2 AT squared. And the fourth and final kinematic equation is velocity squared equals V naught squared plus 2A. Yes. Yeah. Oh, yeah, I knew I was missing something. I'm sorry. So plus 2A times change in position. Okay, so these are the 4 kinematic equations right here. And below right here, I'm gonna write what each kinematic equation is missing. So if you see the first kinematic equation was not included in the equation is position. So you will see that X or X naught is not in this equation. In the second kinematic equation, we will see that velocity, we see V naught, which means initial velocity, but we do not see final velocity. So for the second equation, I will write that final velocity is missing. For the third equation, we will see that we have final velocity, but this time we don't have initial velocity. So that's what's missing out of this equation. In the fourth and final equation, we will see that everything is there but time. So in parentheses right here, I will write that time is missing. And that's important because when we have these questions and we're looking for which equation to use, by being able to realize or see what's already missing, it'll kind of be easy for us to just glance up and see which kinematic equation we should be, which one will work for us. So the first problem that I have written down, it says a light rail commuter train accelerates at a rate of 1.35 meters per second squared. How long does it take to reach a speed of 80 kilometers per hour starting from rest? I'll read the question again. A light rail commuter train accelerates at a rate of 1.35 meters per second squared. How long does it take to reach a speed of 80 kilometers per hour starting from rest? So it's important that when we're working with these problems that we go through and realize what was given and identify what was given. So here you will see that I have the same thing that I wrote up here, just all the variables that are involved in a kinematic equation. Also, as I stated before, all of these things you will find in a kinematic equation, but kinematic equations must always have acceleration. You must always have acceleration. If it doesn't have acceleration, then it's not a kinematic equation. If you notice, each equation right here has acceleration involved in it. So back to the problem. Again, a light rail commuter train accelerates at a rate of 1.35 meters per second squared. How long does it take to reach a speed of 80 kilometers per hour starting from rest? So with that being said, we will just go ahead and start to identify which information was given. So for V initial or V naught, we will see that that will be 0 because it's starting from rest. So the initial velocity is 0 because it started from rest. For the final velocity, they want to know how long it will take to reach 80 kilometers per hour. So that will be our final velocity. 80 kilometers per hour. For acceleration, it says accelerates at a rate of 1.35 meters per second squared. So that is our acceleration. And then for time, that's what we're looking for. They want to know how long it would take to reach that speed. So I'll put a question mark right here. And then right here, you'll see x minus x naught, which is just like the change in position. And that is not mentioned or asked for. So right here, I'll just put an X symbolizing that it wasn't mentioned or asked for. Now, keeping that in mind, it's important that you remember right here when we wrote which equation or what wasn't involved in these equations. So just by looking at this, we could see that this first equation does not mention or does not involve X or X naught. So that's a sign that we can use that equation for this. We know we can't use the second equation because we don't have a value for X or for X naught. So that it wouldn't work because we wouldn't have a value to plug in. Same for 3, for equation number 3, and same for equation number 4. So for this problem, for the first problem, the best equation or the equation that will gear you in the direction of the correct answer would be velocity equals V naught plus AT. And just with this equation, we have all the information that we need to just go ahead and plug this up and solve for T, and we'll be able to get the time, which is what this problem is asking for. I will not solve this problem. I will solve the next problem, but this problem, the goal was just to assist with, helping to identify which equation to use. Now on to the second problem. It says a car slows down from 25 meters per second squared to rest in a distance of 85 meters. What was its acceleration assumed constant? Again, a car slows down from 25 meters per second squared to rest in a distance of 85 meters. What was its acceleration assumed constant? So again, we will go ahead and write down which information was given. So we will write down V naught, V, X, change in position, acceleration. And yes, I believe that's all we have. That's all we have. We could write down time as well. So for V naught, for initial velocity, it slows down from a speed of 25 meters per second squared. So that will be our initial velocity. Final velocity is slowing down, so assume the final velocity will be 0. Change in position, it want to know, it want to reach from 25 meters per second squared to rest in a distance of 85 meters. So the 85 meters will be this value right here. Acceleration, that is not given. And then time is not mentioned or asked for. So again, like I did for the previous question, I will symbolize that with an X. So with that being said, we can go back up, look at what equation doesn't involve time, and that would be equation number 4. So let's look up and see if we can solve that. And in problems like this where acceleration isn't given, you'll just have to solve for acceleration first, and I will solve that. I will show that and then plug it into your kinematic equation. So again, right here I wrote that the fourth equation doesn't ask for time or doesn't involve time, so that would be the equation we would be using, or that's the equation that worked best for question number 2. So I'll go ahead and write that here so we'll know. Velocity squared equals v naught squared plus 2a times x minus x naught. So we'll go ahead and use that. And first, like I said, since acceleration isn't given, we will have to solve for acceleration. And we should know that you would solve for acceleration by doing acceleration equals velocity minus, final velocity minus initial velocity over time. So in this instance, once you go ahead and solve for your acceleration, then you'll have that value, and at this point this wouldn't be a question anymore. You'll have whatever value your acceleration is, and at that point you'll have everything you need to go ahead and plug this in and solve your problem. So I can go ahead and show that. Yes, I'm sorry, I can go ahead and show that. I'm sorry. Just trying to make sure that I was doing it correctly. But yes, I do believe that I identified the which equation to use correctly. The purpose of this video was to just assist with identifying which kinematic equation to use. So I'm going to go ahead and leave that alone so I don't cause any confusion. But by doing what I did, I was able to get the correct kinematic equation to use, and then to find our acceleration, we understand that we could use this right here. On to the next problem, to the final problem. A car slows down uniformly from a speed of 18 meters per second to rest in 5 seconds. How far did it travel in that time? Again, a car slows down uniformly from a speed of 18 meters per second to rest in 5 seconds. How far did it travel in that time? So we'll go ahead and look at the information that we have. We will see that initial velocity will be 18 meters per second. Final velocity, it slows down to rest, so final velocity will be 0. Time will be 5 seconds. It does that in 5 seconds, so time would be 5 seconds. Acceleration, this is another problem where we will have to use this equation right here to solve for our acceleration. So right now acceleration would be a question mark, but this question is very similar to question 2, but the same equations are not used. Yes, so and then you will see that x or x naught is not mentioned as well. Well, the final position is 0. You don't know the initial position is 0. You don't know the final position. Yes, you don't know the final position. And with that being said, this equation will work best. 2 equations actually work for this problem, but the one that I will be selecting for the purpose of this video will be will be equation number 3 right here. X equals x naught plus velocity times time minus 1/2 at squared. So I'm going to go ahead and just write that right here. And again, by writing what was missing, it just assists with quickly identifying which equation you would need to use for, you know, your kinematic problem. Hopefully this video helps and I did it correctly. But yes, that concludes my video. I just went over 3 problems and how to identify which kinematic equation to use. There are 4 kinematic equations, but the problems that I pulled for this video only covered 3 of them. But you would do the same process for, you know, the kinematic equation that wasn't selected for this video, or that, you know, I didn't have time to find a question for to, you know, show how you would get it. But yes, that concludes my video. Thank you.